Aloha and welcome. In this video, we're going to be talking about binary search. In previous video, we talked about linear searching, and we talked about how that was inefficient. And if you had a million elements, you'll have to go through a million different searches and comparisons by the end of it if you have an item that's not actually in there. Well, in this video lesson, we're going to be talking about binary search, and binary search really speeds up this process. So let's go ahead and open up our textbooks. And in here, it talks about the example of a contact list and how it's hard to go through a contact list. You can go through it item by item, and that's going to take you forever. Or you can do this thing called a binary search, and binary search speeds that all up. So we're going to take a look at their example here in the participation activity. So we're going to go ahead and start. And what it does is it divides your entire contact list by half, or it takes the whole size of it, and it divides it in half. And let's say you had 10 elements, it'll go into number 5. It'll look at number 5, it'll say, is this the thing we were looking for? If it is, great, we return it. If not, we say, okay, is this less than or equal to the items on either side? And this is important to remember. So in order for this to work, a binary tree, the list has to be in order. And not only does it have to be in order, it has to be individually, in order to do the comparison, you have to be able to directly access elements in it. So like in an array, you can say array of number 3, of spot number 3 or number 4 or something like that. So the two things that have to hold, one is it has to be ordered, and it has to also be directly accessible. So in this, we've taken our, let's say 10 elements. It's more here in this example, but we have 10 elements. We take the middle element and we compare that element. In this case, it's Mohammed. We're looking for Puja. Puja is going to be greater than Mohammed alphabetically. So then we take the next part. So after Mohammed, we take the list after Mohammed to the end of it, and we compare, or we find the middle element of that one. And then we take that element and we do the same comparison. And if you notice here, we're dividing our search tree by half every single time we do this. So that's what makes this very powerful. So if we had a million elements, we do a search, and that narrows it down by half right there. So this is very quick method of getting through things. So even though a million sounds like a lot, next time it's 500,000, then it's 250,000, 125,000. You can see how this, you can narrow it down really quickly. So anyhow, we go through this process. So in this, it's looking for Puja. It doesn't find it. The middle element is Mohammed. So then it goes on. It throws out that first half up to Mohammed, and it takes the second half starting with Nigel, and it goes and it looks in there. It divides that in half, and the middle point is going to be Sherrod. So Sherrod and Puja, you compare the two. Puja is less than, so it goes back to its previous lower boundary here, which is Nigel. It's going to go to the element up to Sherrod. And that is going to be through Robert. It's going to take the middle element, and the middle element is Puja. So you can see that we've reduced, every single time we do it, we're reducing the search tree by half. So the amount of places that we're searching, it's divided by half, so we can narrow in, we can get to that number really quickly. You compare that to linear. Linear, if you've got something that's in the 500th position in a 1 million element array, it's going to take you that 500,000 searches to get there. In a binary tree or in a binary search, this is just going to take the one access to get to it. So it's really quick. If you were to say, let's say it was at the 125,000 mark, then it's going to, when you look at that, it takes you 2 searches to get to it, whereas it would take you 125,000 with the linear. So you can see the power of this. So now we're going to look in here. Contact list is search for Bob. Assume the following contact list: Amy, Bob, Chris, Holly, Ray, Sarah, and Zoe. What is the first contact compared to? So you take 1, 2, 3, 4, 5, 6, 7, you divide it in half, you're going to get 3.5. 3.5, they're going to 3.5, they're going to round up to 4. So you can check the fourth element here, that's Holly. And then what is the second one you're going to compare it to? Well, let's go ahead and look at this. So Holly, Bob is less than Holly. So we go down here. We have now Amy, Bob, and Chris. The second element will be Bob. So we put in Bob here, and that should be a hit. So, so anyway, binary search, obviously it's a faster algorithm for searching, but it depends on what I mentioned earlier, that it has to be directly accessible like an array, and it has to be sorted, or else you're not going to be able to do this. You're not going to know which way to go, left or right, when you're taking the left path or the right path. So it's going to search, it's going to check the middle element, and it's going to, as it says, if the search key is found, it's going to return that. Else, it's going to look to the left or the right, and you continue narrowing it down half by half each time. So here you look at the participation activity they have, and you're looking for element number 16. So I'm going to go ahead and hit play here. It's going to divide the two. It's going to divide that. So it comes up with 3.5. So it's going to go here. Looking at the fourth item, 16 is not equal to 14. That should be obvious. So the search element, it's comparing the two. Then it changes the low. Notice here it's changing its low and high elements here. Then it goes and it looks at the middle element again. So each time you're iterating through this, you're reducing the search space by half, and it's adjusting what's considered the lower boundary of what it's searching and the high boundary of what it's searching. Then it goes and it finds that middle element again. This time it finds 16 there, and the search ends and it returns 16. So it goes very quickly. So here is the code for a binary search algorithm. So the binary search itself, what you're doing is you've got a low and a high. So these are the boundaries of the area that you're searching. When you start out, you're looking at the 0th element and you're going all the way up to the top of your array. So you're looking at this entire, we're just going to treat it as an array right now. So it's going to take this entire thing, it's going to look at that, and it's going to say, okay, what is my middle point in here? So that's very important. The first thing it does as it's comparing, as long as high is greater than the low, it's going to say, okay, what is my midpoint? My midpoint is the high and the low divided by 2. So I'm looking at that middle element. Then it says, okay, if the value at that midpoint is less than the key, then I'm going to be taking the lower half. So, or no, so if the value there is less than the actual key, then you're going to have to switch. Low is going to be mid plus 1. So you're going to move it to this because we haven't hit it yet. It's going to be in the upper half. So our new low is going to be our midpoint plus that 1 because it wasn't equal to mid. So the new midpoint is going to be mid plus 1. And our high is still going to be the upper bounds of the array. So we're going to keep that the same. So the next time we go through there, let's say that the value at the midpoint then is greater than the key, meaning that we need to look in the lower part of the half that we had left over. So we look at that, but then we're going to keep the low as the same, but we're going to readjust our high to be the new middle minus 1. So go ahead and think through that again slowly. It's what they're doing with the low and the high here depends on where they were previously. So when we first go in here, again, we have the entirety of the array that we're searching. We're going to go in there, we're going to take the midpoint, we take the midpoint over here, and then we say if the value of the element there is less than the key, then we know it's going to be in the upper part of what we have of our array. So then we're going to adjust only the low part because the high is still the end of the array. So then we go from the mid plus 1 to the end of the array. We find the middle point there, and then we do the comparison. We continue in that order. But the other side of that is if we were to take that entire array and we were to get the midpoint, and the midpoint was greater than the key, so then we'd know that we'd have to go and take the lower part of our array. So our new high would be the middle minus 1 because we already searched the middle. So we're looking at middle minus 1. So we're going from the lowest bound, which is the same as before, which is in this case on the first go around 0. We're looking at 0 to the midpoint minus 1. So that's how you implement this binary search algorithm. And then the rest of it is just setting it up. It sets up an array and it prints out the numbers and everything, and then it goes and lets you enter a search thing to search for. So now we're going to take a look at the binary search algorithm execution here using the above code. If we're given a sorted list of all these elements, how many list elements will be checked to find the value of 77 using the binary search? So you have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 elements. You'll take the fifth one because that's 10 divided by 2. So 1, 2, 3, 4, 5. So you're going to be looking at 25 first. So 25 is the first thing that you compare. So it's greater than, so we just did one comparison. So it's greater than, so you're going to take 45 through 114. So 1, 2, 3, 4, 5 elements there. You're going to take, let's see, 5 divided by 2. That's going to give you the 3, the third one, because we're talking about the midpoint. It's the ceiling of the midpoint. So that will give us 77. So it'll take 2 comparisons to get there. So then go ahead and go through the rest of these exercises on your own. Now we get into the mathematical concept here. So binary search, it's incredibly efficient in finding everything. Each time we go through this, as we mentioned, we're reducing the search space by half. So that's very powerful. We're going to be terminating the search once we found the element, or if we find out that the element isn't in there, which means that our search space is empty. So mathematically, for a list of 32 items, if the search key is not found, the search space is halved to 16, then 8, then 4, then 2, then 1. And if nothing is found, it's going to require only 6 steps. So for an n element list, the maximum number of steps required to reduce the search space to an empty sublist is it's going to be the floor of log 2 of n plus 1. So if you remember logarithms, essentially this is going to be for this it's binary, so we're talking about the base of 2. So log 2 of 32. So plus 1. So we're going to be for 32 elements, this is going to be equal to 5 plus 1 is 6. So you just this is the way you can calculate that. And I think they have an exercise coming up that'll have you doing just that. So let's go ahead and look at this speed of linear search versus binary search to find a number within a sorted list. Okay, so binary search begins with the middle element of the list. Each subsequent search reduces the search space by half. Using binary search, a match was found with only 3 comparisons. So if you're looking for 32 in here, in a linear search, you're going to go 1, 2, 3, 4, 5, 6. It takes 6 up here. Down here, we're going to start with the middle element. We've got 1, 2, 3, 4, 5, 6, 7, 8, 9 elements. So we're going to be taking the 4.5 or fifth one. So 1, 2, 3, 4, 5. We start with 11. We're looking for 32. It's not in here, so we start with 32. You can go to 99, and the middle element is going to be 45. It's not that one. So then we take the previous one, the lower half, and then we get 32. So that only took us 3 searches to get there, whereas this one took us 6. And it goes and explains that to you here. So 3 versus 6, we've got a savings of 50%. But again, this is a very small set here of items. As this grows larger, of course, the inefficiencies are much more obvious. So when we're talking about the time it takes for the searches, so if each comparison takes you a microsecond, binary search algorithm runtime is at most 20 microseconds to search a list of 1 million elements. It's going to be 21 milliseconds to do 2 million elements, 22 milliseconds to search for 4 million elements, and so on. So that's why, when you're doing something like a search in Amazon store, it's got 200 million items. That's going to take you less than 28 milliseconds or microseconds. I'm saying milliseconds. I apologize. I mean microseconds for all these. So so it's up to 7 million times faster than linear search. So obviously, linear search would break Amazon. So here we're going to answer some questions about the time it takes. So given an unsorted list of 1,024 elements, what is the runtime for linear search? Remember, this is linear, not binary. So you have to go through each one. So that's simply 1,024 times a microsecond. And that's going to be 1,024. And then, this one, I'll let you do this one because this is going to require you to do the log. So if you take your log function back there, you'll figure that out. 10 to the 24, you can do the math, but that's 2 to the 10. So if you've got 2 to the 10, you can go and plug that into the formula up above. And then down here for binary search, this is just going to have you exercise. I'll do one, let you do the rest. So list of fruits is search for banana. You're looking for banana here. You've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 elements. So you're going to start at the fifth one. So the fifth one, the first one search is going to be 1, 2, 3, 4, 5. So we got lemon. And then the second one is going to be search. So lemon, we're looking for banana. We know it's in the first half. So then we take this section here. We divide it in half. It's going to be banana. So banana should be the second one that we search for. Check. And that is correct. So it's going to have you answer questions like these for 2 through 5, just to make sure you've got that. So anyway, that is it for binary search. Remember a couple things here. One, in order for binary searches to work, it has to be an ordered list. It has to be in order. The second thing is the elements of it have to be directly accessible so that we can do a comparison using just one. We can go directly there. And the other thing is the mathematics behind this. Know that the binary search is extremely efficient compared to linear search. It's when we look at our formula to calculate the number of searches necessary, it's going to be the floor of log 2n plus 1. So yep. So that's all you really need to know from here. Do keep in mind what happens when you have an array that has an uneven number, an odd number like 7. You go to 3.5, but you go take the fourth element. You're going to be rounding up on that. So that's all for binary search. If you have any questions, feel free to reach out. Send me an email. Let me know. I can set up a meeting to talk it over with you. Otherwise, I'll see you in the next video. Aloha.